Hello, everyone. Welcome to the Moscow Telecommunication Seminar. Our today's speaker is Egor Endovitskiy. Egor Endovitskiy has received bachelor degree in applied mathematics and physics at the Moscow Institute of Physics and Technology last year. His bachelor thesis was devoted to the experimental study of capture effects in smartphones and Wi-Fi access points, and the main contribution was the development of a USRP-based Wi-Fi testbed. Currently, Egor is a research intern at the Wireless Network Lab at the Institute for Information Transmission Problems and first-year master student at MIPT. Today, he will tell us about the approaches to model the wireless channel in modern MIMO systems. Egor, the floor is yours.
Thank you. Thank you for introduction. My presentation will consist of two parts. The first part will be about modeling single input, single output feed-in channel. I'll start with the fundamental notion of tap delay line. Then we'll tell about relay and receive fading and when they emerge. Then I'll tell about two implementation, TGax model and filtered white Gaussian noise. Then I will move on to MIMO fading channel, TGN and QuaDRiGa. The first one uses some techniques from CISO fading channel generation, so the first half is also useful. So let's start. Now start with tap delay line. The first thing to grasp is that wireless channel is modeled as a linear time-varying system. In particular, a combination of delta function. It's left upper picture. So it is a time-varying impulse response. What is the motivation for such model? For a signal, there might be multiple paths to get to receiver, several reflectors, several scatterers. And what is a nature of time dependence in such model? For instance, a moving reflector. If a reflector is moving and it reflects the signal that is shifted according to Doppler shift. It may get closer or further, so path loss changes that coefficient. And a direction to reflect itself changes, so it changes accordingly due to anisotropic radiation pattern. So we have a time-varying impulse response, and that yields given input, it yields output Y of t. And accordingly, we can define a time-varying frequency response. Now, it is a convolution of inputs exponential function with the sum of delta function. So the response is a sum of exponential function with the slowly varying amplitudes and phases. How to work with the tap delay line? There are two variants. The first one, when we need a channel in a frequency domain, and correspondingly to the definition, we just need to evaluate the right formula at a set of chosen frequencies. The second variant is when we need a channel in time domain, in discrete time domain, for example, for waveform simulation. We may use a sampling theorem, given that the waveform is band limited. We may represent our signal as a certain series. Time-varying impulse response for the discrete system effective can be written as this. This is the second formula on the left. And the resulted waveform if we pass discrete symbols, is given in a form of FIR filter. So one way to create a single input, single output fading channel is time varying tap delay line, which coefficients change through time and delays. So we can change them in accordance to some fading processes. There are two general fading processes. The first one is relay, and the second is racing. They both model multipath reception for removing antenna from stationary statistical point of view. The first scenario on the left corresponds to relay fading. There are a lot of random identically independently distributed reflections or such that central limit theorem works. And they some which with each other. And we are asked with the question, what is the resulted envelope distribution and what is going on with the channel? When the velocity of antenna equals to 1, the envelope is distributed to according to relay distribution. The question might arise, what it has to do with the time tap delay line. Now, the single tap, and I remind you, tap is a coefficient near delta function, is a sum of many multipaths components that are not resolved by receiver. A handy example is a tree. It has many leaves and many occurrences of reflections take place simultaneously, but they are certainly not resolved by RX ADC. So an temporal evolution of tap can be modeled like this. Now, the second variant is rising fade, and the scenario conceptually is the same, but there exists one dominant component, and it is usually considered deterministic. It corresponds to, for example, a line of sight path. And again, when velocity of antenna equals to 1, the envelope distribution is rising. And the parameter of the distribution is the ratio of powers between loss component is highlighted and others combined. Now, important thing to take from this slide before we move on to implementation of such concepts is that relay fading can be transformed to rising fading. How? Look at, if you may, the formula at the left bottom. The key that K is a sample from relay fading channel. Now we add to it a deterministic component that is weighted by K factor. So this is deterministic component, and the other is the same because they differ only in one component, deterministic. So that was the conceptual idea. Now moving on to implementation. Now the question may arise, why do we need to implement if we have a relay distribution? The thing is, it's easy to calculate analytically the case when speed is 0 and it yields a relay distribution. But the channel is statistically flat. It means that it has no frequency selectivity. Now, moving on to TGax model. It is a way to generate a relay fading process. And I remind you, we need to just generate just a relay fading process because racing is constructed by adding deterministic component. Now, TGax model is a basis for all sum of sinusoids methods. What is the essence of that particular method. The model is following. In the center of unit circle, there is a receiver which moves with a speed v. And on the very circle, there are uniformly distributed multipath components that sends their reflection to the receiver. They don't alterate the amplitude, so the amplitude is the same, but they add first the random phase, which is taken from uniform distribution. And then there is a Doppler shift, which is determined by the angle between a velocity and a direction to multipath component. So the fading process in such model is given by two components, real and imaginary. It's a complex process. So Doppler shifts are given by such formula because they are uniformly on circle. F max is a parameter for Doppler fading. It is maximum frequency of Doppler shift. Now, the real part is obtained by summing cosine function, and the imaginary part is obtained by summing sine functions. It is worth noticing that that particular model, though very popular, is rarely used without modifications due to its drawbacks. First of all, it has non-zero correlation between real part and imaginary part. The second, which is worse, there is non-zero cross-correlation between pair of waveforms. So even if we obtain random phases, those fading processes will be somehow correlated. And later in the presentation, we will need to generate a lot of such processes. Now, moving on to alternative method, and I will remind you that if those fading processes are applied to coefficients in tap delay line. The second method that implements a fading process is called filtering white Gaussian noise. The steps to do are following. At first, a complex uncorrelated Gaussian process with zero mean and unit variance is generated in discrete time. Then such complex Gaussian process is filtered by a Doppler filter with the appropriate frequency response, which equals to square root of desired Doppler power spectrum. Those Doppler power spectrum are different for different scenarios. Here are two pictures of Doppler power spectrums. The first one on the left is called bell-shaped Doppler power spectrum, and it is more frequently used in scenarios where surrounding objects are moving. And the second one on the right is a so-called horn-shaped Doppler power spectrum, and it is more frequently utilized when receiver and transmitter are itself moving. And it's called TGax spectrum because it implements Doppler power spectrum from TGax model. Question from Artem Krasilov. Could you please explain what is the Doppler power spectrum? What is its physical meaning? Thank you for the question. Now, the answer is following. It's a spectral it's a spectral power density of a stochastic process that is obtained when signal is passed through Doppler fading channel. It means that its physical meaning is the following. For example, in JX model, it can be easily more handily understood. Suppose we have an infinite number of multipath components, and each adds its small contribution. They have different but discrete Doppler shifts, but their contribution differs from frequency to frequency. So it's a spectral density of random process. Which component is stronger? I don't know. Another way to tackle it. Suppose we pass a sinusoid with a particular frequency, and it's reflected from many paths components, and it's somehow we obtain output signal. Now we may calculate its power spectrum and average over realizations. So those are random, and the resulting spectrum would be a Doppler fading spectrum. That's the physical meaning.
Excuse me, just to clarify, so for the JX model, what will be the shape of this Doppler power spectrum for JX model, for example?
Well, I don't have a formula with myself, but it's one shown in the picture on the right picture.
Okay, so JX model corresponds to the right pictures, like horn.
Yes.
Okay, thank you.
Thank you for question. I shall continue. So let us commence forth. Yeah, TGN channel model uses filtered wide Gaussian noise technique, and it uses actually a second component, not only bell-shaped, but a second component in certain profiles. It corresponds to component due to moving vehicle. So yeah, TGN uses filtered wide Gaussian noise technique. Now let's move to MIMO fading channels, and we'll start with the TGN channel overview. So a set of taps and their powers is given in the document, and this is a table from the document. And let me emphasize that there are excess delay, raw, and power. So this is a tap delay line, so that we can construct a tap delay line. Now, a reminder, before I will tell the idea how to generate MIMO channel from several CISO links. If tap is n-loss, so it doesn't have a dominant component, then it's a complex Gaussian variable with certain power. And notably, relay distribution is the magnitude of complex Gaussian. And without Doppler fading, it is flat channel relay without Doppler fading. And Doppler spectrum, Doppler fading, is obtained by filtering that Gaussian variable through corresponding filter. So the idea of how to generate MIMO channel in TGN and later channel models like TGAC, TGax, because those are iterative versions of TGN. The idea is following: generate n takes times nRx IID complex Gaussian variables with 0, mean, and 1 power. Nx is the number of transmitting antennas, and nRx is number of receiving antennas. Then we transform them into same number of complex Gaussian variables, but correlated in a meaningful way, so that correlation between them corresponds to some spatial properties. And then we apply Doppler fading as a single input, single output case. So this is an idea for TGN channel. Now let us move on to a little bit of details. Now, in general, for each step of MIMO channel, the matrix is separated in loss and loss components. Now, even first step can be subjected to recent fading. So it depends on recent K factor. But its multipath components are not resolved by our ADC. So it is possible, and actually it is measured, that some of main taps actually have some recent behavior. So for each tap of MIMO channel matrix, it is separated in two metrics. The first one corresponds to, it is fixed, and it corresponds to loss component, which is deterministic. And as you can see, they are weighted according to a K factor. The second one is a set of IIDD Gaussian variables to be correlated. The actual correlation due to the very properties of Gaussian variables can be done by multiplying on spatial correlation matrix of the channel. So this is a formula for creating a set of correlated Gaussian variables, because they are determined by mean and second moment dispersion. Now the question is how to obtain this matrix. And a gentle reminder, it is a correlation between every pair of channel links for a given tap. There is a conjecture. A conjecture was made, and in fact, it was proven by some experimental research that a certain approximation might have right to exist. It's called a Kronecker approximation, which approximates spatial correlation of the channel, of MIMO channel. Now, that matrix is that matrix equals to Kronecker matrix product of RTX and RRX, where RTX and RRX correspondingly correlation matrix of transmitter antenna array and receiver antenna array. Now, the Kronecker product, matrix product, is in some way of extension of outer product of vectors for matrices. So the dimensions are in order. And conceptually, it's Kronecker matrix product is a multiplication of every element of matrix with every element of matrix of second matrix. So it's conceptually. Now, in TGN channel, we need to obtain those matrices. That's why some geometrical information is written in that table. For there is a certain fact from general physics that those matrices for particular type of antenna, for uniform array, can be calculated using power angular spectrum. Now, what is power angular spectrum? Roughly speaking, it is a distribution of power from of angle from a particular cluster for particular tap. So because a gentle reminder, a tap might be a sum of non-resolvable in time multipath components. So the angle of arrival of signal from that certain tap might be not fixed. It might have some shifts, I mean, in angle. And this is included in that very model. So power angle spectrum in that model has truncated Laplacian shape. What does it mean? It means that the class, the tap is reflecting signal in some 3D angle. And its maximum is defined by angle of arrival, mean. And the tolerance is defined by angle spread, the receiver, and correspondingly transmitter. It is a variance of truncated Laplacian shape. Now, it was shown that angle of arrival and angle of departure can be taken at random from uniform distribution, and they are fixed in a table for reference purposes, because correlation matrices are already calculated for those angle of arrival and angle of departure. Now, it is handy to take a break here and to explain the difference between clusters and taps. Now, the taps are combined in clusters because they have a similar distribution of angles. So they have similar angle spread and similar angles, maximum of those distributions. So because for every antenna a cluster is fixed, there is, and those correlation matrices are calculated for all antennas. We obtain, a gentle reminder, we obtain a correlation matrix for the channel, so we can create MIMO links. And as for details, that's the end. Now, that was a correlation of channel among different antennas in antenna array. Let's shortly discuss how MU-MIMO is implemented. Now, there is a quote from TGac channel model addendum, but the very essence of it is that they add some angle diversity, which means that they randomly, for every client, for every receiver, they randomly change those mean angle of arrivals and angle of departure randomly, and that adds angular diversity. As a result, RTX and RRX, and those are correlation matrices, are different, are slightly different for each user. But power delay profile is the same, so in some way they are connected. A question from Vyacheslav Loginov. Could you explain how the coefficients in TGN were achieved in slide 11? E.g., the power difference of different tap in cluster, it is some interpolation of real experiments or some analytical model was used? It is interpolation of real experiments. Yeah, thank you for the question. Now let's move to a completely different model, but that uses the same approach. So a gentle reminder, it still presents a channel as a tap delay line. The essence of that model, which is called QuaDRiGa is that it is a so-called statistical tracing model. It actually doesn't perform ray tracing, but it, first of all, it distributes clusters randomly in accordance to statistical parameters defined in scenario, distributes in space, stores some geometrical representation of clusters, for example, an angle of arrival from cluster and angle of departure. Those are geometrical representations and power coefficients. What's more important, all parameters of resulted tap delay lines for every link are calculated based upon positions of clusters, plus the interpolation of antennas radiation patterns. It facilitates MIMO because a natural correlation between links of different antennas naturally emerges because though coefficients of tap delay lines are different, they originate from the same set of clusters. And to elaborate, statistical parameters of clusters, what are they? First of one is delay spread. Its formula is written here. As you can see, there is a summation over a delay and a power of delay. K factor is, as a reminder, is a ratio between loss component and no loss. Loss means line of sight, and loss means non-line of sight. Angular spreads, QuaDRiGa is 3D model, and it tracks both azimuth and elevation angles. This is roughly speaking the same as delay spread, but for angles. Now let's slightly move to details. Now QuaDRiGa uses two-step. It's a stochastic model, as I said, so it generates clusters randomly, but it does so in two steps. Maybe next slide would be handy, but I will return to the previous slide in a minute. So some information is taken from scenario, a large scale fading is generated, and then it influences small scale fading. Now let's track those differences for delay spread. Now delay spread is integral characteristic. So it characterizes some statistic of cluster set. And in scenario, TGPP and so on, there are four numbers. The first one is important is, delay spread, being a large-scale fading parameter, is generated using log norm distribution for every position of receiver. The parameters for log normal distribution, ds mu, it is a mean, and ds gamma variance. And the third parameter is ds lambda. It defines how fast the ds varies through space. It means it is useful for MU-MIMO because if we play, because in QuaDRiGa, if you place two users near each other, their large-scale fading parameters will be, for example, delay spread, will be correlated based on the distance. And the order of such correlation is ds lambda. It's a part of scenario. Now, that was a large-scale fading parameter. Moving on to small-scale fading parameters, what are those? Those are a particular set of clusters because they actually define small-scale fading. And there is a corresponding parameter, which is called st lambda. What is this? It's a decorrelation distance of all random variables used for generating the small-scale fading. Now, to slightly elaborate, let's look at that flow chart. So ds, it's obtained from log normal distribution using scenario parameters. It's a large-scale fading parameter. Then it is used to alternate randomly generated small-scale fading parameters, which are actually clusters. Clusters have some delay, which is tau, and this is summation over different carrier frequency. It's not important here. So QuaDRiGa rescales randomly generated delays so that the desired delay spread from large-scale parameters is obtained. So that was spatial dependence part. But what about temporal fading? Now TX and RX they move through space. In QuaDRiGa, you have to actually write it down with a specified trajectory and speed, and the vector speed is tangential to trajectory. There are two variants in QuaDRiGa. You can switch between them. The first one, all clusters are generated, but they will be close to the old ones because of the spatial correlation of LSF and SSF. Those are being large-scale fading and small-scale fading, because TX moves a little. The second variant, clusters are the same, and their geometric representation is just recalculated. Because if a transmitter moves, then and cluster stays where it was, angle of arrival changes, angle of departure changes, and so on, and probably a power changes. So this concludes my talk. Let us recap. There was firstly a general representation of Farrell's channel tap delay line and methods to obtain such tap delay line. Firstly, for case of single input, single output fading channel. Those are filtered white Gaussian noise and some modifications of some of sinusoids. Then methods for generating MIMO fading channel. The first one was to combine correlated seesaw channels, and second one is statistical ray tracing models. So that concludes my presentation. Thank you for listening.
Thank you, Egor, for your presentation. I have two questions. The first one is for which technologies both of the model of MIMO models you mentioned are usually used? And the second question is, could you somehow compare both models, some advantages that, for example, some model can do that the other cannot? Thank you.
Okay, thank you for the question. So the first one, the QuaDRiGa, I suppose, is more suitable for cellular network simulation because it actually implements some specification, some abstraction of model from 3GPP. So it suits better. Now, in the contrary, TGN and TGax model suit better Wi-Fi simulation because they are standardized by corresponding working topic task groups. Now, answering the second question, the drawback of QuaDRiGa model is it has no transparent way to model fading, because sometimes it's not convenient to create a trajectory for every user. Otherwise, it's not possible to obtain a fading in QuaDRiGa in its default configuration. But it has a advantage when compared to TGN model. It has some interpretable MIMO correlation, because those are the same clusters, but seen from different antennas. On the contrary, in TGN model, first of all, the Kronecker approximation is not that accurate. The error is about 10%. And the second, those correlation matrices are calculated for uniform linear array, and that is restriction. Hope it answers the questions.
Yeah, thank you.
Thank you. And the question from Dmitry Bankov: are there any existing unsolved problems related to with model MIMO channels? What could be possible directions of research in this area? There were several articles devoted to how to add fading channel into QuaDRiGa-like models, which utilizes clusters. The problem was, the solution that was proposed is time dependence of existence of clusters. So the process of birth and death, but the problem is that it's very hard to measure the effective rate of such things. So the problem is how to get a convenient fading simulation in such model that have particular special characteristics. Okay. Thank you for the question.
I have one more question. The question is, for which frequencies these models can be applied, or it completely does not depend on frequency, for example, for terahertz or something?
I don't know. So the question, those models have the limitation. It might be connected with the, so scenarios for the first model, they were extracted from certain experiments, and they have certain frequencies. So the answer is yes. It's an open question whether they can be applied to higher frequencies, but I'm afraid I'm not. I can't swiftly answer that question fully. What's the nature of such restrictions? Maybe, yeah, maybe because of faster, bigger frequencies, the number of taps will be increased significantly. So there might be computational difficulties.
And I guess my last question for today, could you tell something about, do we have open implementation of these models, or if we want to use it, we have to develop it from scratch?
QuaDRiGa model is open source. TGN model, as I remember, the closed source. They have been implemented by MathWorks. Some of sinusoids with the different modifications is also open source.
I guess that's all. Igor, thank you for your interesting presentation. Thank you for all the participants of this seminar. See you soon.